The Faraday's law problem of a rotating loop in a constant magnetic field can be solved in two different ways. The first way uses the standard sort of general form of Faraday's law, where the induced EMF is minus the time derivative of the magnetic flux through the loop. The second way of solving this problem uses the motional EMF method, where the induced EMF is the integral around the loop of the effective electric field dl, where that electric field is U cross B. We'll look at the first way first. If the area, we'll look at the first method first, and that's the one where we're finding the time derivative of the flux. Now, if the area of the loop is staying the same, but the direction of the unit of the vector normal to the loop is changing, then what we end up with is that the flux, which is equal to the integral over the area of B dot ds, where ds, if we say that up is in the z hat direction, ds is going to be z hat, let's say, cosine of omega t. And I'm going to have to the right be x, so it's going to be plus x hat sine of omega t. That means that it goes, it's rotating clockwise. I drew it counterclockwise. No, I drew it clockwise. Okay, good. All right. So if I have this time-dependent direction on ds plus multiplied by the magnitude of ds, which gives me my differential area, and the direction of the magnetic field itself is not changing, then the flux is going to be the total area of the loop times the magnitude of the magnetic field, assuming that the magnetic field is constant, which it was, times z dot that time-dependent unit vector, z hat dot that unit vector, which gets me cosine of omega t. So V EMF is minus the time derivative of that flux, which is equal to omega A B naught sine of omega t. So that's one way of solving this solving this problem.